Let's look at the voltage load for a practical electrochemical cell. It is a system with zinc anode and nickel oxide hydroxide cathode in an alkaline solution. Okay, so let's first look at the so-called electrode reactions. The anodic or the oxidation half-cell reaction would be for zinc metal to combine with hydroxy groups to form zinc hydroxide and release 2 electrons. Let's check balance. 1 zinc on the left, 1 zinc on the right. 2 oxygen on the left, 2 oxygen on the right. 2 hydrogen on the left, 2 hydrogen on the right. Minus 2 charge on the left, 2 electron, which is minus 2 charge on the right. So this anodic half cell or oxidation half cell reaction is balanced in terms of both mass or weight and the charge. Then the cathodic or the reduction half cell reaction on the nickel side electrode would be for nickel oxide hydroxide to combine with one water molecule and one electron to form nickel hydroxide and generate an OH group or hydroxy group. Again, mass balance 1 nickel, 3 oxygen, 2 plus 1, 3 oxygen, 3 hydrogen, 2 plus 1, 3 hydrogen, minus 1 charge on the left, minus charge 1 charge on the right. So the cathodic or the reduction half cell reaction is also balanced. Okay. If you want, you can try to write the full cell reaction. And don't forget, when you go from half cell reaction to full cell reaction, you have to make sure there's no electrons left in the overall reaction. Okay, so for such an electrochemical cell, the kinetic parameters are given in this table. So we have different parameters. Symbols. The first column is symbol. The second column is the value and the unit for the different variables. And the third column is for the physical meaning. So RANI means the surface roughness factor for nickel electrode. And for nickel electrode, this value is 100, which means for example, 1 centimeter square projected area, the actual electrode area may be 100 times higher. Ra zinc, the surface roughness factor for zinc electrode is much lower at 2. Okay, which means for a projected area of 1 centimeter square, the actual electrode area is roughly 2 centimeters square. Okay, J0 Ni means exchange current density for the nickel or for the cathode, nickel cathode, and it is at 0.61 amp per square meter. And the J0 zinc exchange current density for the anode or zinc electrode is at 60 amp per square meter. Of course, these are projected area. Okay, so the actual number to get the current density, you have to multiply this roughness factor by this exchange current density number to get the effective exchange current density. Okay, and EEQ, that's our equilibrium cell potential for this nickel versus zinc electrochemical cell. Nickel oxide hydroxide / nickel hydroxide pair versus zinc hydroxide / zinc pair. The electrochemical equilibrium cell voltage would be 1.74, which means when there's no current passing through, you would measure a voltage of 1.74 volt, assuming no internal leak and one electrode reaction on each of the 2 electrodes. And alpha A Ni and alpha C Ni are for the anodic and cathodic transfer coefficient for the nickel electrode. And remember we said earlier in the text in quite often. Earlier we were using beta for the symmetry factor and n for the number of electrons, and quite often the beta times number of electron transferred n would give us the alpha C value. Okay, and alpha A and alpha C add up for nickel would be one electron transferred, which is the same, one electron transferred for the cathodic or nickel electrode reaction. On the other hand, alpha A zinc and alpha C zinc are for the anodic and cathodic transfer coefficient for the anode or the zinc electrode. And here the two numbers are slightly different, 1.5 for anode and 0.5 for cathode. And again, if you add these two numbers, they should give you 2, which is the number of electrons transferred for the anode or the zinc half cell reaction. Okay, and again, it's beta times n gives us the alpha C for this number. And kappa would be the electrolyte conductivity for this electrochemical cell. And in this case, it is 6 Siemens per meter. Siemens is just 1/ohm, and the electrical conductivity would in this case be 60 Siemens per meter. And L would be the electrolyte thickness, and this one is very thin, around 2 millimeter. So with all these kinetic parameters, we want you to determine first the cell potential, the external cell voltage, the cell potential at a galvanic current density of 1000 amp per meter square. So the effective current density going through the cell with zinc side going through oxidation and the nickel side going through reduction would be 1000 amp per square meter of projected electrode area. That's the first part. Knowing the current density, we want to determine the overall cell potential. The second part is to determine if you know your total cell voltage. Your total cell voltage, which is somewhat lower than one equilibrium cell voltage, which means we are in galvanic cell mode, discharging, converting chemical energy into electrical energy. And if the external cell voltage is 1.3 volt, we want to know the discharge current density. Okay, and then as we mentioned before, this alpha A would be 1 minus symmetry factor beta times n, while alpha C would be symmetry factor times n. And for example, the zinc electrode, the n would be 2 and the beta would be 0.25, and that would give us this number. And for the nickel electrode, n would be 1 and beta would be 0.5, then that would give us the cathodic transfer coefficient for nickel electrode. Okay, so this is our problem. We know what the electrochemical cell is, what is the anodic or oxidation, what is the cathodic or reduction half cell reaction. We know some basic kinetic or electrochemical parameters, and we want to know, if we know the current density, what will be the cell voltage, and on the other hand, if we know the total cell voltage, what would be the effective current density. Okay, so that's our problem, and in the next few slides we'll examine how to solve these two problems.